Hi, I'm Lior Wolf from Mentee Robotics, and I will speak about AI for humanoid robots. So if you look at AI as of 2024, it seems as nothing cannot be done. Progress has been just amazing, much faster than anticipated. There seems to be a convergence. Everybody's using the same transformer models. And if you look at the major challenges of AI, computer vision, NLP, speech, all of these have seen a lot of progress in the last few years. So the question is, what's left? And the answer is general purpose robots. And the reason is that AI is very good at learning from data. But in order for robots to be successful, you need to learn from experience. However, collecting experience for robots is slow and not very safe. The solution, work inside of a simulator. However, there is a gap between the simulation and the reality. And overcoming this gap is a major challenge that you need to solve if you want to be practical about AI in robotics. So we started Mentee Robotics in January 2 years ago. And the reason that we thought that now is the best time is due to a few revolutions in AI. So one of these revolutions is the one of large language models. Large language models allow you to communicate in a very natural way with the robots, but that's not all. With a large language model, the robot can self-reflect. The robot is trying to grab something, it fails, it needs to do something else. So you cannot program all these edge cases. The large language model is a very good way to create the scripts that actually run the robots once it realizes what it has to do. A second revolution is one that we mentioned, is the one of working inside of a simulator. Working in a simulator, you can collect infinite amounts of data and train on whatever task you want to train on. However, you need to bridge the gap between simulation and reality, and I would like to convince you later on that Mentee Robotics has been able to overcome this gap. A third revolution is the one of foundation models in computer vision. So for example, Mentee is using the latest models in order to perform open vocabulary queries and detect objects, whatever object, it's not limited to a closed list of objects. Another revolution is the one of semantic 3D models. So models such as NeRFs and Gaussian splatting, together with semantic information, allow us to model the 3D world in a very accurate way that also supports querying and searching inside of these models. The last revolution is the one of compute. Every one of our Mentee bots runs two NVIDIA Jetson Orin GPUs. This allows the robot to run all the different AI models that allow the robot to interact with the world in a very natural way. So what is unique about Mentee Robotics? Mentee Robotics is an AI-first company. We develop all the AI models here, and we integrate many different AI models in order to create a robot that can perform tasks in the real world. This includes reasoning, includes navigation, includes locomotion, dexterity, and so on. Many different capabilities that are integrated in order to support the applications that we would like to support. So we say that we are an AI-first company, but we also do everything here. All the mechanics, the actuators, the electronics, and so on. This is done by Mentee Robotics. So let's start with a small demonstration of what we mean by overcoming the sim-to-real gap. What you see here on the right is Tesla Optimus Generation 2. This is a very sleek robot. It looks great, but the way that it's walking is basically starting by bending the knees and then making very cautious step-by-step in a straight line. It can make turns, but these turns are not very natural as well. On the left, what you see, this is the Mentee bot, our robot. It's not as sleek or well-designed, but it can walk in very natural gait with straight knees, and it can walk forward, backward, sideways, make small turns, turn in place, squat, and so on. And the underlying reason for this natural gait is that Mentee bot is trained inside of a simulator. Everything that Mentee bot knows how to do is learned in a simulator. And then by overcoming the sim-to-real gap, we are able to apply it to the real world. So this was the lowest rung of the ladder, the one of locomotion. At the top rank, we have the cognitive model, the one that takes a task and breaks it down into subtasks. So what you see here on the right is the way that the task is being broken down into API calls. So MenteeBot hears a task, understands it, and with a large language model, breaks it down to a list of API calls. These API calls are actually in Python. Here you see it as English text just for visualization. And if you see a command such as locate the kitchen table, it calls for the 3D semantic model and searches this model for the kitchen table. What you see on the left is that it found the kitchen table. This is the red dot. The robot localizes itself inside the 3D model. This is the blue dot. And then it can navigate to the kitchen table. So before showing the actual video, let me just say that in order to complete a task, you need to integrate the reasoning, the locomotion, dexterity, navigation, and everything together needs to be well integrated and work together. And I'm going to show you now a video. This is an edited version. You can go to our website or YouTube channel and see the unedited end-to-end video. All the videos that we release are end-to-end because this is the major challenge. How to have the task actually performed in one go as a continuous way that the robot takes the task and just performs it. So let's see the edited version.
What would you like me to do?
Hey Mentee, please go to the table in the kitchen and wait for instructions.
Okay, I will go to the table in the kitchen. I have arrived. What should I do now?
Please put the fruits in the container and place it on the counter behind you.
Sure thing.
Thank you, Mentee.
So what we just saw was an integration of between 20 and 30 different AI models. Some of them we take off the shelf, but this is the exception. Speech to text, text to speech, this we take off the shelf. Everything else is being done inside of Mentee Robotics. This includes the fine-tuning of the large language model, includes the open vocabulary queries for detection, the 3D modeling of the world, which is done with a semantic layer, the locomotion that we already described, and so on. Everything is a different AI model trained in a simulator where possible, and then integrated in order to create this end-to-end capability to perform a task. And the emphasis here is on the end-to-end task. We don't show you bits and pieces, different capabilities. We want everything to work together, and integration is key in order to make everything work. A second thing that it's important to notice is that when you actually perform the task end-to-end, there are many things to worry about. So for example, if you need to navigate to a specific location, then it's very challenging in bipedal robotics to synchronize the legs such that you arrive to the exact position so that you can reach in the right heading and so on. Also, coordination is key. When I'm reaching for something, my entire body needs to balance my motion and maintain stability so I can perform the action with the hands. Same when I'm carrying a weight. So integration, as I said, was a challenge, but now that we have a stable platform, hardware and software, we can develop new capabilities. And the next video that we're going to see is the one about Mentee's first day in a new place. So Mentee is using a 3D semantic map of the world. And in addition, it uses a dynamic map of the occlusions that exist right now. This is using stereo vision. And then MenteeBot is able to navigate these two maps together. However, when we get to a new working place, we need to map this place. The most natural way to do it is for MenteeBot to track a person, follow that person, and then the person would show MenteeBot around, show the place, point at things, and so on. This is what you are going to see in the next demo. MenteeBot following a person. What is following? Following is going to the current position of the person, but the person continues to move. So we need to track this in a smooth way, and this is what you are going to see in the video.
Hello, my name is Mentee Bot. What do you like me to do?
Hey, Mentee, please follow me.
Sure, I'm going to follow you. What can I do for you?
Please face me.
Face me
Sure,
basically
I'll face
means
towards you.
to maintain the person in the center of the field of view by turning in place.
I'm waiting for your instructions.
Please walk backwards.
Sure, I'm going to walk backwards. I'm waiting for your instructions.
Please turn in place.
I got your instructions. I'm going to turn in place. How can I help you?
Please walk sideways.
No problem. I'm going to walk sideways. What can I do for you?
Please squat.
Sure, I'm going to do a squat. How can I help you?
Thank you, Mentee. That's all.
You are welcome. It was my pleasure.
So let's talk a little bit about different approaches that exist toward AI and explain the exact approach that Mentee believes in. So let's start with the distinction between a compound AI system and an end-to-end AI system. End-to-end system is one that trains directly on data, going directly from the sensor information, from the pixels, to the actions. This is end-to-end system, and you can think about the early natural language processing systems, the early language models, they were end-to-end. And many people tend to think that ChatGPT, for example, is still an end-to-end system, taking in tokens, outputting tokens, trained in a semi-supervised way on large corpuses of data. However, this is not the case. There is a shift from an end-to-end AI model into what is called a compound AI system. A compound AI system combines multiple components together in order to support the needed performance. For example, if you ask ChatGPT to multiply two numbers, it wouldn't just use text prediction to know the output. It can do it, but it wouldn't. It wants to be accurate. So what is being done is that ChatGPT would write a short Python script and then run this script in order to obtain the result of the calculation. Similarly, if you think about automotive, so Mobileye recently made in a blog post the claim that it's much better to use a compound AI system that detects objects, for example, and then makes the decisions on top of these detections. The alternative for using an end-to-end requires much more data that includes a lot of edge cases. So for automotive, some companies may say that it's required to have end-to-end. Some of them would say that the compound AI system might be better. But we claim that whatever the situation is for automotive, for robotics, we have to use a compound AI system that combines multiple components. In order to explain this, let us make a small distinction that exists in statistics. And this distinction is the trade-off between bias and variance. So bias is what is also called the approximation error or the training error. You have your training data. You train a model on this training data. You fit the model. And then you measure the error that you have. This error is what is called bias, or approximation error, or a training error. Variance is what is also called the generalization error. Is when you move from the training set to test data, your error would increase. This increase in the error, this gap, is what is called the variance. So if you think in terms of bias, what is better, a compound AI system or an end-to-end system? The answer is that with an end-to-end system, you simply increase the capacity of the neural network, and you can fit any data that you want. So if you think just about bias, just about being with a very low training error on your training set, then an end-to-end system is the right way to go. However, if you think about variance, and this is about the edge cases and about things that you didn't see inside the training set, then having a network with too much capacity would overfit your data and might not generalize well for the new examples. However, in a compound AI system, you look at the data, you break it down into components, and then you make your inference on top of components that you were able to identify. So the decision is the same decision most of the time, whether it's training data or test data, and you are able to generalize better. So those who believe in end-to-end training, what's the best way to reduce variance that exists in such systems? The answer is to collect more and more data. However, in robotics, this is very difficult because the action space of humanoid robots is very large. There are 29 degrees of freedom, even without the hands. You have 29 degrees of freedom in the body. So you need a lot of data in order to cover enough of this space of motion that you want to cover. Also, the tasks that you are doing, the environments, everything has a lot of diversity. This is a general purpose robot. It needs to do all tasks that humans are doing. It needs to work in any environment. So there's a lot of variability. And collecting enough data to cover all of this in an end-to-end system seems to be impossible. If you compare this to automotive, in automotive you have millions of cars driving around, recording data, and the action space is relatively limited. There are only a few degrees of freedom that you need in order to navigate the world. So the situation in robotics calls for a compound AI system, and this is why in Mentee Robotics we take multiple components and we combine them in a very practical way in order to create a robot with a true AI. Another thing that has to do with what is the best way to learn robotics is the distinction between the way that actions are being learned. So in Mentee Robotics, we use reinforcement learning inside of a simulator. Most of the training occurs offline. We have clusters. These clusters run simulations. We collect a lot of data, and we train the AI policies that control the robot in runtime. Just like learning how to ski or any other complex skill, it takes time, experience in order to learn the task. But once you learn it, it's automatic. At runtime, these networks are extremely efficient. They run on a real-time CPU and allow us to maintain a high level of safety. Another approach that some other companies are using, it's called model predictive control. In model predictive control, you have a world model or a simulator running as the robot is operating, trying to predict what would happen if some action is being taken. So there's a lot more compute involved, and you need a much more accurate model of the world, which makes the robot much more expensive, and it also requires you to know what is the weight of what you are picking and what are the physical properties of the environment. A third approach is the one of control theory. Control theory basically means that a mathematician models a task, and then this is being programmed into the robot. This is limited in the way that mathematicians have limited capacity to create locomotion and other type of motions. You need to model the world or make some approximations. If you bend the knees, the robot becomes much more similar to a pendulum, and then you can use pendulum equations. However, this limits the type of motions that you can perform, and it's also very hard to add new motions. So as we said, Mentee Robotics is a proponent of reinforcement learning inside the simulator. So let's talk a little bit about how to overcome the sim-to-real gap. And let's start with a thought experiment. Let's say that I have some policy that can make your robot walk in the real world. And I make the robot take some steps in the real world, and I record every action that was taken by the robot. And then I take the robot, I put it in the same initial position, and I play the same sequence of actions. What is going to happen? What is going to happen is that after a few steps, the robot is simply going to fall. And this is because there is a lot of noise in physical systems, and no two runs are exactly the same. So you need to adapt to the situation. You can't have a fixed control policy running the same actions again and again. Let's have another thought experiment. Let's say that I can have my robot walk inside of a simulator. And I have the robot walk inside of a simulator. I record the actions that took place. And now I go to the real world, and I play the same set of actions when I initiate the robot in the same position. What would happen? Well, the robot would obviously fall, as before, because it doesn't adapt to the situation. But the point is that the robot is going to fall much faster than earlier. And the reason is that the simulation and the real world behave differently. The physics inside the simulator, no matter which simulator, no matter the quality of simulation, and so on, it's never going to be a perfect match to the real world. This is the gap between the simulation and the reality. If you think about a simulator takes the current state of the physics world, the action that you're going to take, and then it predicts the next state. So it's a mapping between a state and an action to the next state. What is reality? Reality is very much like a simulator. You have the current state, you have the action, and then you move forward in time and get the next state in the real world. The problem is the sim-to-real gap is the difference between the next state that occurs inside a simulator and the one that happens in the real world. So as machine learning guys, we might think, well, can you overcome this by just learning the gap and then compensating? So there is a gap that is a function of the state and the action, and then you learn this gap, and you just correct for this gap. So this might be possible, but it has a few technical issues. This is not natural to learn inside a simulator. The information that you need to expose is one that you don't necessarily get from the simulator, and it's not going to be perfect. What we suggest at Mentee Robotics is something else. We suggest to manipulate the action space in order to make the simulation and the reality fit better. So imagine that you have an action that you want to take. You have a network that adapts this action, slightly modifies it, such that the gap between simulation and reality is being reduced. And then we take the problem of minimizing the gap between simulation and reality, and we transform it into the problem of learning an action policy. In this case, the corrective action policy. And learning policies inside of a simulator is very natural to do. So let's go through the various stages, starting from the basics. So how to use reinforcement learning for learning locomotion. In reinforcement learning, you have the state space, you have the action space, and you have the reward. So in the case of locomotion, that state space includes the position and velocity of each one of the actuators, each one of the degrees of freedom. And you use this information together with the IMU information in order to know what is the current state of the robot. It's also very convenient to add the desired heading and speed of the robot into this state space, because the same network is going to get this information and then adjust the behavior of the robot. The action space is the desired position of the actuators in the next time frame, in which way you would like to move the actuators in order to continue your motion. And lastly, the reward includes the rewards of the type of not falling, walking in a way that is symmetrical, having a smooth walk, adhering to the commands of direction and speed, and so on. Almost everyone who tries to minimize the sim-to-real gap is using what is called domain randomization, adding noise to the simulator in order to be less sensitive to the difference between the simulation and reality. We do this as well. We can talk for maybe an hour just on the way that this is done in Mentee Robotics, but this is not the current emphasis. Of course, we do domain randomization when we learn how to work inside of a simulator. The question that I would like to address is the one of collecting real-world data and then using the real-world data in order to improve the simulator. So let's say that I learned inside the simulator, applying domain randomization and other techniques, I learned some initial policy. And I can use this policy in order to make a robot work in the real world. And I then collect the data from the real world. What is the data in the real world? It's a sequence, starting with a specific state. I apply some action. I get to another state in the real world. I apply some action. The action is with the policy that I learned in the simulator, but I record it in the real world, a sequence of state, action, next action, and so on. So once I collected this data, what can I do with it? There are a few solutions in the literature, such as SimOpt, real-to-sim-to-real, and so on. And mostly what they do, they try to augment the parameters of the simulator in order to better fit the reality. So these systems exist. They worked, for example, for robotic arms and so on. They were not shown to be effective for legged locomotion. And we tried such techniques. For us, at least, these techniques did not prove to be very effective in minimizing the sim-to-real gap. What we do instead is that we learned a corrective policy which adapts the action that we want to take such that the sim-to-real gap is minimized. Given an input of a state and an action, it returns a term called C. This term C is the corrective term. Instead of taking action A, we take action A, we add the corrective state, and we get a new action. Then the simulator is being applied with the new action, and it is learned with a reward that minimizes the gap between simulation and reality. So once we learn this corrective simulation, we are able to retrain a policy in a simulator when we apply a corrective term. The corrective term that we apply makes sure that the sim-to-real gap becomes narrower. After we learn this new policy, the improved policy, we apply it in the real world. When we apply it in the real world, we apply it without the corrective term because reality doesn't need to be compensated for. Reality behaves like reality. And we can show that working this way, training with a corrective policy, improve the results. So this specific work, what it contributes is that it provides a sim to real and back to sim method that is effective for legged locomotion. It improves the simulation by correcting the action space. It's learned like any other policy using reinforcement learning in a simulator, and we can actually measure the improvement that we get for bipedal gaits. So what you see in this video is that we take what we learn inside of a real session and we play it in a simulator. The robot falls almost immediately. Then we try to use supervised learning to bridge the gap between simulation and reality. This improves a little bit, but it's not very effective. The robot still falls pretty fast. Then when we apply our method for correcting the policy and play the real data inside of a simulator, the robot can continue to work because this learned policy minimizes the gap between simulation and reality. And if we look at the obtained motion, what you see here is the very first robots that we had, called version 1. Then you can see that you get the walking pattern that is a lot more symmetry than before. If you zoom in, you see that the gait, the way that you step, is much more natural than what you get if you don't apply the corrective term. And we have a bunch of metrics to demonstrate that working in this way is much better than not using a corrective term or trying to use a supervised way to bridge between simulation and reality. whether we are talking about the symmetry of the motion or the heading, and so on. So we talk about AI, but I would like to make some very important point, that a robot runs on software, and the software is as important as the AI, and it has multiple layers. It starts with the embedded software that runs all the actuators and control the IMUs and the communication and so on. On top of it, what we have is a physical layer. The physical layer is the one that handles all the communication with the embedded software. On top of it, one layer up, we have the core. The core is the one that runs the policies on top of all the signals that it gets from the physical layer. In addition, we still haven't discussed much of it. We have the perception. We have the mapping of the world, the localization inside of the map, the navigation, the occlusion maps, the depth, the occupancy, the detection. All of these are multiple perception tasks that we need to run. And on top of it, we have the brain of the robot. The brain runs the large language model in order to take the requests and what is needed to be done and break it down into API calls that controls all other layers, whether it's the perception and the core and so on. So the way that our system is designed is that we have the motion controller. This is a CPU that runs real time, runs the action policy that we learn inside of the simulator, and there's important safety features and safety layers running on this real-time CPU. In addition, we have two Jetsons. One of them is dedicated to the core perception tasks, such as the handling of the camera information, the state estimation of the location of the robot, and so on. And the other one is used for the other tasks, such as running the large language model, the voice, the computation of the NeRF, and so on. And very important for the development is that we have a perfect digital twin. So we have a model of the robot, including all layers from embedded, physical, core, and so on, implemented together with the physical simulator. It's important in order to have a perfect model and overcome the sim-to-real gap. It's also important for debugging. Everything we do, every change, needs to be debugged before we actually run it on the physical robots. So let's now turn our attention into the topic of navigation. And navigation might sound simple in the sense that you have Waze or Google Map or anything else. You're able to know your path and navigate over there. You have cars in the real world that park themselves. Might look like an easy task. But actually, it's much harder for bipedal robotics when you need to synchronize the legs together with the position, the exact position and heading in which you need to follow. And navigation is actually something that has three different layers. At the topmost layer, it's like Waze or Google Map. You need to know where you are. You need to know where you're going. It's a graph search problem. You search for the optimal path that you want to take. At the lowest level, there's the control. This is going forward, backward, sideways, turning, and so on. And then there is a layer in between, which is the path following. This needs to bridge between where you want to go and the commands that you send to the robot. The list of commands needs to be sensible. You cannot make turns in place instantly and so on. You have the momentum, you have the motion of the robot. You need to bridge in a smooth way. You need to synchronize your steps such that you would arrive at the right location. So the navigation layer, this takes into account the NeRF-based map of the world. This is the static obstacle map. You have the dynamic map. You get from stereo vision, you get occlusion. You build a graph together with both of these in order to go from where you are to the goal that you need to go to. You use a modified AI star algorithm in order to build this path. This path is given as a list of next positions, which the path following policy needs to take as input, and then it issues a list of commands that are being sent to the robot how to walk. There are actually two path following policies. One of them is a policy that is good up to 1 meter. So this is a less accurate policy. If you are 1 meter or more from your target, you use this one. you go very efficiently, and it's only approximated with regards to the heading. The second policy is very exact. You need to get to the exact position in sub-centimeter accuracy with the exact heading that you want to get, such that you're able to reach, such that you're able to grab something from the right place that you need to stand. And what you see in our demos is actually the combination of these two policies together. The first policy would give you a very fast way to walk. For example, the following demo that we showed, that you follow a person. What is following a person? It's navigating to the correct position, but this position changes all the time. So for this, we use the first following position. And then there's the final approach. In the final approach, you need to get to the exact position. So you synchronize your steps. Some of the steps you take sideways, such that you get to the exact position where you need to get in an efficient way and a very stable way. Let's talk a little bit about perception. And perception, as we mentioned, has many different components inside. So there's the NeRF mapping of the world. There's the ability to search inside this semantic 3D model of the world. There is the ability to localize yourself inside this model. And together with visual odometry, tracking of the visual data as you go, you estimate the exact location of the robot. This is called state estimation. This is, as we said, is an input to the navigation and also to the final approach when you're trying to get to the exact location and trying to plan the way that you walk and the way that you control the robot. In addition, there is a way to locate items in 2D image. Once you see the image, this is not inside the 3D model. This is once you see a specific desk, what are the objects that exist on the desk, and then take this information and lift it to 3D so that you can grab this while avoiding obstacles. Obstacles, both when you're walking and when you have a walking area that you need to reach with the hands, it's a topographic map that tells you these regions you can enter, these regions you need to avoid. So some of the components that we use are components that we take from other foundation models. However, we need to run them very efficiently on our GPUs in real time in a very high frame rate. So what we use is what's called this model distillation. We take a large foundation model and use a smaller network in order to make it more efficient without losing a lot of accuracy. Some of the models that we use combine different capabilities. For example, when we are trying to take a 2D object and bring it to 3D, we combine a 3D point cloud together with a segmentation model that is called NanoSem. Some of the objects use NeRFs, but we augment these with visual embedding that we are able to also use in other parts of the system. I will talk about it in a few slides. And there is components that are very unique to what we are doing, such as state estimation, which fuse the NeRF localization with the visual odometry in a way that is unique to our needs. So as we said earlier, there is a topographic map that tells you if you're walking, these areas you need to avoid. This is based on stereo vision. Similarly, for dexterity, there's a walking area. You need to know from where to reach the object and grab it while avoiding the various obstacles. This information from the topographic map goes directly into the various RL policies that determines the actions that are being taken. We use NeRFs and Gaussian splatting in order to model the 3D world. What is a NeRF? A NeRF is a neural network that given a point in 3D and a viewing direction gives you a color and opacity. The way that we perform mapping and localization with NeRFs is that we first build a NeRF of the environment from the video data that is being collected. And then we apply what is called superpoint in order to find interesting points that we can later on identify and track on the NeRF models. And then we learn how to position ourselves by what we see from the camera in relation to the superpoints that exist in the 3D NeRF. So this allows us to run an algorithm that is called RunSack for matching between the superpoints in the NeRF model and what we see in the actual image. We run this every couple of frames. We also have the ability to track continuously the position. And this is the way we are able to position our robot in the coordinate system of this 3D semantic model. Every point in the model has semantic information, not just the RGB information, but also information that can allow us to query what is an object. We can search for the oven, we can search for the refrigerator, and so on. Everything is from an open vocabulary search. We don't need to define the list of objects before. We just need to embed the information in the 3D model and then have various queries. The way that we do it is similar in a sense to what is called NeRF. NeRF is like a NeRF that has another component, which is semantic features. So in the original NeRF, they used dino features for regularization and clip features for querying. The way that this is done in our system is that we don't use multiple scales. We use segmentation of the actual objects that we obtain using SEM in order to embed the objects. And the embedding that we use, it's not clip. It's something that is based on the OWL version 2 model that we use for distillation and creating for 2D queries. So we have a uniform way to embed visual information across 2D, 3D, real images, and 3D models of the world. By doing it this way, we're able to improve performance in comparison to the baselines. So let's talk a little bit about what is required in order to build useful robots. So Mentee Robotics already is able to integrate multiple components and create a robot that can perform many tasks. But some components are still missing. So let's go over the list of what is missing and how we plan to overcome it and which steps we already took on the way to overcome it. So this is the map of what we want the robot to be able to do. We called it the functional design architecture. Everything we want the robot to be able to do in order to be useful. It has components that we already discussed just a little bit. For first day in an office, this is called onboarding. The robot is coming to a new place. It needs to map it by following a person. The person is going to point at different things, whether it's a place, whether it's an object, and the robot needs to remember this information for later on use. There are direct requests. This we already saw. But there's also the agent behavior. What is an agent? An agent is an AI that you loosely define the task. You don't give the task very specifically. And the AI needs to figure out what to do. We have many of the required capabilities, but some are missing. For example, we need to be able to respond to events, and we need to add this capability. And object manipulation, this is something that we are constantly improving, for example, for opening doors, calling elevators, and so on. So tracking a person, this we already demonstrated that we have. It's about detecting a person, and then tracking a person between the views, so you track the same person all the time. Sometimes you lose the tracking. You need to re-identify the person among multiple people. This is called re-identification. It's not implemented yet. It's done with face recognition and with the colors of what the person is wearing. You need to be able to approach the person, basically go to where the person is. This is being done using the path following RL policy that we discussed. And you need to stop. When you reach 1 meter from the person, this is your cue. You need to stop at this place. The face me capability that you saw earlier, it's about maintaining the person inside the center of the field of view, such that the person can show you new stuff. Once you go after a person, you collect the visual data. You need to build the 3D model. This is something that we currently do not on the Jetsons themselves of the robot. We want to add it inside the Jetsons so that when the robot is resting, it would be able to perform this computation without requiring an outside computation. So let's talk a little bit about the pointing interface. The person might point and say, this is the main elevator, or this is the biggest box that we are using, or this is where we store empty places. In all cases, it's going to be a point, and it's going to be a text that the person is going to give. But it has different semantic meanings. In some of the cases, this is about specific locations. In some of the cases, this is about specific objects. So you need to understand which one of these cases is the case that is being applied. And this is not very challenging. You do it with a large language model, and you ask for this distinction between these different cases. Then there is the pointing interface. You need to look at a person, track the skeleton of the person, track the end of the figure, see where the person is pointing to in 3D. This is already implemented. We have it. It's about tracking the pose of a person and then lifting this information to 3D. If the person is pointing at an object, you need to remember the way that this object looks like. This is about visual embedding, and this is something that we do in multiple parts of the system already. The other type of learning is remembering that there is a certain place that you need to know in the map, or there is a certain concept, and so on. This you do by learning in-context information that you later on put into the prompt of the large language model. So we also talked a little bit about agent behavior. For this, you need to self-reflect. We have this capability in a limited way. If we try to do something and we fail, we realize this and we try in another way. But we also need to add triggers to events. For example, go to a specific place, wait for something to happen. This requires the ability to be triggered by a future event, which we need to add to our system. Object manipulation is very important. There are multiple types of object manipulation. Some of them are, for example, press a button. What is press a button? Is detect a button, realize which direction and which force you need to apply, and go and apply this action. This is about combining visual models together with language models in order to control an RL policy that provides this capability. Other set of capabilities, such as opening doors, you have multiple types of handles. You need to learn this based on imitating a person performing this action. And this is done by mapping pixels to action space and using a technique that is called imitation learning. Let me finish by talking about the ability to handle a falling robot. So our policies are very robust. The robot is working in a very natural way. It doesn't fall for no reason. It's able to stand in a very stable way to perform action as needed. It's able to carry weight and still go, and so on. However, sometimes there are obstacles. Many of the obstacles that exist on the floor, we see them, we go around them. Sometimes we step in an obstacle, we train inside a simulator as to not to fall, but in other cases, it's unavoidable. We actually have a model called S4 running on the robot, detecting when the robot is about to fall. If the robot is about to fall, and you can correct for it by standing in a stable way, switching into stable standing, this is the best way. If falling is unavoidable, you want to make sure that you become very soft, and you fall in a very soft way that is safe for the robot and the environment. So safety is a major concern, and there are things that the robot is responsible for. However, the robot needs to be safe also in adversarial cases. If somebody tries to make the robot fall or tries to trick the robot in any way, the robot should still maintain a lot of safety. So that's what I prepared for now. Thank you very much for your attention. If you have any question, just please email me. I'll be very happy to discuss any topic about robotics, AI, or anything else. Thank you very much.